As in the previous lecture, we have been going through to the basic characteristics of the crystal detector, and also the uh, PIN diode photodetectors. That means the detector side and modulator side. That is PIN and modulator, and there was used a detector. Okay, the modulation and detection part. Okay, so there are long calculations going through to the square law. That is the famous Taylor series of the voltage, and as you can see, that is the Taylor series. And if we just put the value of V as the AC signal value then you can get the series like that. So after calculating, we get the square law becomes clear. So there is you can see there is you can see that this in this part there is a square law that has been obtained. Okay, after calculating it with given AC signal. So now, going through to the part like that, in addition to the detector circuit, this is the equivalent circuit of a detector. That is the equivalent circuit of the detector. So as we use in detector circuit the low pass section, that's a diode, and the high pass section of the filtering. So that is one of the equivalent circuit detectors. And that the R naught and C represent the impedance of the junction, and R is the body resistance of the diode. A figure of merit of a detector is the voltage, and the current sensitivity of the detection function is expressed as voltage sensitivity is equal to R naught ITC divided by pi n, that is the input power, and current sensitivity is the short unit current, and R naught divided by R plus R naught, and pi n is the power. So there is a part of sensitivity all along with it. And here is the tangential the sensitivity of a detector. So the minimum signal level, that is an important question. The minimum signal level of a diode can detect depends on the noise in the diode. The ability of a diode to detect a signal is the presence of noise is called tangential sensitivity of a detector. A graphical illustration of the concept of TSS is sketched below. That is the graphical representation or concept of TSS. Okay, that in that oscillator we get this kind of voltage waveform. Okay, so if it is a detector side, if we take it as square wave, there are some waves under it. Okay, just like a modulation, as you see in the AM modulation, same as that detector, amplifier, and oscilloscope, we will get that from the pulsed signal. So that is the experiment procedure. So first of all we have to connect the power supply with the Kahn oscillator, and then a square wave generator to the PIN diode modulator, and the both blocks of Kahn oscillator and PIN diode modulator will have to be connected. Then we will connect the variable attenuator part to calculate the uh, impedance, and also how much attenuation has been taken place. And there is a crystal detector to detect the microwave power, and what is the microwave frequency running now, we can detect by the crystal detector. Then we should just connect it to the oscilloscope. So that is the setup equipment. And we have to apply 9 volt to the Kahn oscillator, and we have to set the variable attenuator to the 10 dB. So first of all we have to set 9 volt plus 9 volt actually, and we have to set the variable attenuator to uh, 10 dB. So adjust the square wave generator to, that is the square wave generator, that means we have to verify the square law. to 1 kilohertz to 2 volt peak to peak output. Connect the generator to the PIN modulator, then that is the PIN diode modulator. Okay, and that is the crystal detector. We have to find out the operation of both in a circuit, in a one circuit. So after adjusting the square wave generator, then we have to adjust the scope, that top of the square wave aligns to the zero level to the screen. That means we have to adjust the scope and adjust the attenuator so that the bottom of the square wave aligns to the zero level on the screen. Repeat above measurements for 1 volt peak to peak. That means we have to repeat the example, repeat the assessment from 2 volt to 1 volt negative square wave, and calculate the modulation depth of the two modulation inputs, 2 volt peak to peak and 1 volt peak to peak, using the following equation. Here V max is for the 2 volt peak to peak and V min is for the 1 volt peak to peak, and we have to measure the value and put it there. Then we will get the attenuation out of that, and we have to just check the value of attenuator, it is right or wrong. And that is the equation of modulation depth. As you can see, V max equal to mu min minus 1, V max equal to mu min plus 1. M is the modulation of depth. As I have as I have said, that there you can see that is the input of that in input section of it's a modulated output, and the input section of crystal detector. And as we have used the diode in the crystal detector, and the biased there is diode, and there was high pass filter, as you can see, sorry, low pass filter, as you can see, to find out the output from it. So as one can see, that attenuator setting deviation A can be expressed as is the P max divided by P min, and V log V max divided by V in. The square law characteristics of a crystal detector. To find the square law characteristics, that is the setup of crystal detector. It is the power supply to the gun oscillator, square wave generator. In the PIN diode modulator, there is a fixed attenuator, there is a variable attenuator, and waveguide to coaxial adapter from waveguide to coaxial adapter to thermocouple mount, and there is a power meter. Okay, now we have to check the power, and just not assume but also check it at once. So you can now also check in the same kind of as you can see the connections, there are some changes in that part. There was waveguide to coaxial adapter and thermocouple mount, and just change the output section with variable attenuator, just the crystal detector to find it out and SW inductor. So select the range of the meter and adjust the gain control SW and meter to obtain the potential reading of the decibel scale. So there is a chart of SWR calculation. So whenever the gain changes, if you change the gain from